Alright, in this video I would like to review first of all what the rules are for the behavior of a conductor, and then also talk about a new case that we hadn't really considered before, which is what happens when the charges are actually flowing in the conductor. So to begin with, suppose that we have a conductor like this. And we want to know what is the electric field in the conductor. Well, the rule that we have is that the electric field equals 0 inside the conductor. And the reason for that essentially boiled down to if the electric field were not 0 inside the conductor, then charge would be moving. And since we are interested specifically in the static case, we don't want charges to be moving. While things are changing, it's complicated in any number of ways, which we're going to explore soon. But for now, we have wanted the charges to be more or less wherever they're going. Okay, so essentially the argument here then is that if the electric field is not 0, then it's not static. Okay, so the electric field is 0 inside the conductor. We also found that if there are excess charges on the conductor, then they will move to the surface. And the reason that they had to do that was because of Gauss's law. So if they didn't move to the surface, then there would be some electric field inside. So I can draw a Gaussian surface that's really close to the actual surface of the conductor. And if there was any charge inside that surface, then I would not get a flux of 0, and the electric field would not be 0 inside. Okay, so excess charge is on the surface. And just as a reminder, we can represent a surface charge density with the Greek letter sigma, which is just the charge divided by the area that it is spread over. The third rule that we had for conductors is that the electric field is perpendicular outside the conductor. And so essentially what that looked like is if I draw some field lines here, then they're going to always start out perpendicular, but then they're able to spread out as they move away. So they don't stay perpendicular, but when they leave the surface, they're going to be perpendicular. Okay, sort of like this. Okay, and we can actually understand this a little better now with the fact that you have solved the electric field for a charged sheet. So if we have a charged sheet, what you found is that the electric field just points directly away from the sheet, and the magnitude is constant everywhere along the sheet. So this is with positive charges I've drawn. And that makes sense now if we think about the surface of the conductor having some sort of charge density, which over some small enough region is going to look basically uniform. You'll get an electric field like this. All right, so you might wonder, now wait a minute, what about the inside part being 0? That's not consistent with what I've shown here. Well, let's say that we have two sheets, for instance, the two sides of a conductor. Oops. So I'll draw a second one like this. And we'll imagine that that represents the far side of the conductor. And suppose that there are some positive charges on that side as well, like this. Well, it will also have an electric field, some pointing up and some pointing down, like this. But then inside, those two electric fields will cancel. So the blue electric field points down, the green electric field points up, and when we do superposition on those, the electric field inside becomes 0. Okay, so in a more realistic conductor where it has some shape, it isn't two infinite sheets, it's not as clear exactly how that'll happen. It'll in general be some really complicated charge distribution, and somehow the electric field will cancel out everywhere inside the conductor. But if we imagine it as being say a long thin metal plate, then we can imagine that the excess charge goes to the two surfaces, and we can see how those would cancel inside. The final rule that we had for conductors is that the potential is constant on a conductor. All right, and the explanation for that was pretty straightforward. So essentially, we have a formula for the potential difference between 2 points. It's negative the integral of E dot ds along some path that we choose. And if we choose some path between any 2 points inside the conductor, the electric field is 0. So that's the integral of 0 times ds, which just comes out to 0. So if there's no difference in the potential between 2 points, that means that the potential is constant. Okay, so these were all considering the static case, but what happens if we have a non-static case? All right, so there are multiple ways that can happen. Let's imagine that I change the electric field. So, I have my conductor and I change something externally, so the external electric field changes. Well, then the conductor is going to respond by having some charges move. So anytime we have something change in a situation, we'll get charges flow. All right, and so in this chapter and the next couple of chapters, we will be studying what happens in that flow of charge. So in particular, we want to define a new quantity that we call current. And the variable that we use for current is I. And I is just the amount of charge that flows in some amount of time. So you can either think of that as Q over T, or if you want dq by dt, because it could be varying in time, and so that might be, in more complicated situations, you may have to use the derivative form. So what are the units for current? Well, we can figure it out from the formula. We're going to get units of charge, which are coulombs, divided by units of time, which are seconds. All right, so 1 coulomb per second is 1 amp. Okay, so the full name of this unit is the ampere, but typically people will just refer to it as an amp for short. So you've probably heard that unit before. It's named after a French physicist, Ampere, so that is another unit named for a person. The actual symbol is capitalized, but as is the case with every SI unit, the full name, if you write it out, is written out lowercase. All right, so one comment I want to make about the unit in amp is that this is actually a pretty ordinary sized unit. In everyday applications, it is perfectly reasonable to have an amp of current. The appliances in your home probably use anywhere between, milliamps and like maybe 10 to 20 amps. Something like a dryer probably has the highest usage in your house. It may be, a couple of dozen amps. But, a normal appliance like a clock probably is using like milliamps or less. And other things are going to be in between. So it's a perfectly ordinary everyday sized unit. Some of the units we're going to encounter in the study of electricity are going to be enormous units, and some of them are going to be extremely small units. This one happens to be a very practical size.